Alright, y'all, so tonight we're going to be going over exam 2 for spring 2024. Of course, this is EM, Applied Electricity and Magnetism, and this problem is going to really be a Faraday's Law problem. And of course, we're going to be applying KVL to solve this. Now, the first thing we really have to know is, I guess we have to read the problem, right? We're given H and we're given the current, and you'll notice that the H vector is a function of current. Now, this is important later on in part B, but just make sure you remember this. Now, it's asking here, find a formula for what the sum of the four voltages will be. Of course, we know as electrical engineers, this is not a difficult problem to solve. However, we're going to be doing, the physics really of solving this, the physics way of solving this instead of the electrical engineering way. Now, how do we go about doing this? Sorry. The way we're going to be doing this is we're going to be choosing a closed path. Of course, KVL is the sum of the voltages on a closed path. So we're going to be choosing a closed path, and we're going to be going counterclockwise. We're going to be going like this. Counterclockwise. You could choose clockwise. This is up to you. What will happen is the polarities will change. Your answer will not. So you choose whichever way. I'm going to go with how Dr. Jackson did it, counterclockwise. So hopefully this is okay. Now, using Faraday's law, and you can find this in Notes 18, page 24, we can see that V of t, of course, a time-varying voltage, is equal to the negative derivative of the magnetic field, denoted by this trident. Maybe I can write this, maybe I can draw this kind of well. That's good enough. Is equal to the negative derivative of the magnetic field through the loop. And you'll notice I put a little z here. Why is it z? This is important, especially in notation. Dr. Jackson is notorious for taking off points for small notation errors. And you'll notice the z direction is because when you do right-hand rule for the current, remember, your current is going in the counterclockwise direction, and your thumb will be going in the direction of the magnetic field. Or I guess not in the direction of the magnetic field, but your thumb will be pointing up. The magnetic field would be going in the direction of current. So the direction of current that we've chose, or the magnetic field, will be going counterclockwise. So your thumb will be pointing out of the screen or in the positive z direction. This is how you choose, or not choose, but that's how you identify which way it's going. Remember how I said polarities will change if you chose clockwise. If you choose clockwise, which way will your right hand, which way will your fingers be going if you chose clockwise? Well, your thumb will be going into the screen, or in the negative z direction, and your fingers will be going in the clockwise direction. This is what I mean when I say polarities will change. However, we're going in the positive z direction, counterclockwise, so we let this be here. The negative will stay. That is an inherent part of the equation. The only thing that will change is whether it's you'll get a negative or a positive answer for your z value. Okay, anyways, now, what is this? What is this magnetic field part? Like, what is this weird equation? Well, on the same page of the same notes, Notes 18, page 24, we can see that trident in the z direction is equal to the integral, the surface integral, of the b in the z direction, ds. Remember, this is a surface integral. And now, well, we don't know what bz is. We don't know what b is. By Maxwell's equations, though, we do. We know b is equal to mu naught h. And remember, we're going in the z direction, so they are components, not vectors, components of a vector. And we apply hz. Now, we know what hz is. We know h of t. Of course, it only has a z component, so we only have to worry about that. But now we can say b of z is equal to mu naught, the time varying current, divided by 2 pi y. And of course, amps per meter for h of t. Okay, but now what can we do? Well, we can plug this back into this integral, because now we can take an integral of it. And that's something we know. Now we know what b of z is. So let's say this is now equal to the mu naught, because again, this is a constant, of the double integral. Why double? Well, we have a surface integral. Surface integrals are double integrals of I of t over 2 pi y. And now we have to figure out, how are we going to integrate this? What are we going to integrate this over? Well, in our case, we're given an xy coordinate in our Cartesian plane. So we're going to say dx dy. Now, what are the bounds for x? We will say that x has a little bit of a starting point. We'll call this x. And we'll call this w, right? So we have x is equal to, well, x is equal to x. Then x is equal to x plus w. The distance from here to here. Right, we're going from x to x plus w, is essentially what I'm trying to say. Now, on the bottom one, we're going from h, y is equal to h on the bottom, then we're going to the top, y is equal to h plus l. You have to take into account all of it. Now, we've created our bounds, we've created our integral. Now it should be an easy integral to integrate over. We are going to do this. So this is going to be equal to mu naught over 2 pi. Remember, 2 pi, they're all constants. All we're left with is, I guess I of t actually comes out also, because it's not a function of x or y. Yeah, it's not. So then we do the integral. We can put parentheses. Integral of, we'll start with y. So h and h plus l of 1 over y dy times the integral from x to x plus w of dx, because there's no x's. Now we take the integral. This is a very easy integral. This is natural log of y evaluated from h to h plus l. And then this one here is x evaluated from x to x plus w. This will end up being natural log of h plus l minus natural log of h, or natural log of h plus l over h. And then this other one, it is what it is. This other one right here will become x plus w minus x, which is just w. Now we go back and we plug this in. What do we get? Well, we get mu naught over 2 pi I of t times natural log of h plus l over h times w. What is this? What do we find? Remember, we haven't found v sum. We found this magnetic field. We found this trident. Excuse the terrible drawing, but this is what we found. Okay, so now what do we do? Well, remember, v sum, or the voltage, is now going to be equal to this, but the negative derivative of it. So negative d over dt of the entire thing, which is mu naught over 2 pi I of t natural log of h plus l over h w. Now, we're taking it with respect to time t. Which part of this changes with time? Well, definitely not the constants, not natural log of h plus l over h, or w, only the current. So we're going to rewrite this as mu naught over 2 pi natural log of h plus l over h times w, and then we'll take the negative on the outside, the derivative of I of t with respect to time. And what is I of t? I of t is I naught cosine omega t. We'll write this down here. The derivative of I of t is equal to I naught, the derivative of cosine is negative sine. And remember, we're taking it with respect to t, not omega t. So we have to multiply the entire thing by omega, chain rule. Now, we can replace this here. We can replace this part into here. So now v sum of t, or your answer for part A, is equal to, remember we have a negative here and a negative here? They cancel. So we're left with mu naught, I naught, omega, w, divided by 2 pi, and the natural log of h plus L over h. Let me make sure this is right. Oh, I forgot the sine of omega t. Again, let me make sure this is right. This looks right. So we have mu naught omega I naught w, natural log, sine omega t over 2 pi. Perfect. And don't forget your units, volts. Here we go. So that's part A. Now, that doesn't mean we're done with the problem. Of course, we have part B. And I'm going to show you two different ways. One is, of course, the electrical engineering way. Really, they really are both the electrical engineering way. Question 2 says, or asks us to solve, assume that each of the 4 elements in the loop are resistors. Find a formula for the voltage V1 as a function of time. Now, we have the sum of the voltages, so I'm going to draw this out in a way that might make sense to most of y'all. Let's say we have V sum of t. And now we have resistance here, resistance there, right? And we'll just say it's connected to ground, right? Both of them. So we have a loop. We can have a loop like this, just like we've done over there. So this is plus minus V1, plus minus V2, plus minus V3, and plus minus V4, right? They all have the same, voltage drops. If what I'm looking at is the polarities, so we're going in clockwise direction, so we're hitting, they're all voltage drops going from positive to negative, positive to negative, positive to negative, and positive to negative. So they all have the same polarity. We can leave it like this, but we're only looking for the voltage across this V1. We're looking for V1 really. So we place a voltmeter across it. Now, there are two ways about going through this. We can find the current, which we know, I of t, and say, remember this is R1, we can say V1 of t is equal to I of t times R1. And R1 should be 1 mega ohm. Yes, 1 mega ohm. So we can say 1 times 10 to the 6th I of t, right? And remember, the problem only states that we want to find a formula for voltage V1 as a function of time. This is voltage of V1 as a function of time. There we go. Another way you can do this is you can use the voltage divider rule. You can say that V1 of t is equal to the sum, V sum of t times R1, because that's the voltage we're trying to find across R1, divided by all of them added up. And of course, this is just the voltage divider rule. Either way will get you the same answer. They will be correct. They should be correct. But either way, if you know the current through a resistor, you can find the voltage across it. If you know the sum, the entire voltages, the sum of the voltages across each resistor, you can find a voltage across a single resistor. So hopefully this made sense. Make sure you always put your units. I'm notorious for missing this. Hopefully this helped y'all, and it makes sense about how we're going to do this. We're going to do multiples. A lot of these Faraday's and Lenz's law questions. This is usually the first question on an exam, so y'all should definitely be masters, or at least know how to do it by the time the exam rolls around. So hopefully this helped, and I'll see you all in the next one.